Hello everyone. Our presenter today is Dr. Milad Ramezani, a current research scientist with the Robotic Mapping and Understanding team at CSIRO Data61. He completed his PhD at the University of Melbourne. Afterwards, he did his postdoc for 2 years and a half, roughly, at the with a dynamic robot systems group at the Oxford Robotics Institute. My actual postdoc for that 2 years and a half, and following that, he joined CSIRO. Welcome.
Thank you very much. It is a true pleasure that I am here at ACFR. This is the first time, and I am really excited, to give a presentation about, my recent works. Mainly, those works over the course of 3 years when I joined CSIRO, and I worked on 3D scan, lidar scan, and then try to incorporate deep learning in different components, especially loop closure and place recognition. As you see, lidar place recognition, deep multi-robot re-localization, and post-graph attention network I will describe later on. So a little bit about my background. I had a great opportunity to join the Oxford Robotics Institute 2018 to 2021, where I had the opportunity to work on different robot platforms, animal version B that time, as well as a handheld device. So on top of this device, we collected a large data set in one of the colleges at Oxford, New College, and then we decided to put the name New College data set. So you can, if you are interested, just check out this data set. I believe it is broadly used in the community, and I am really happy about that. And I had a chance to be involved with some PhD research projects conducted at ORI, led by Yidlo, who is a postdoctoral research fellow at ACFR now, and Matthias Matamala on the topic of visual teach and repeat. I believe he's a postdoctoral research fellow at ORI. Correctly. So I'd like to start with this work, which was my main topic during my postdoc at ORI. The task was development of a light 3D lidar slam deployable on a mobile CPU. Those CPUs available on animal. One of the CPUs we use for perception tasks like slam, and in a kind of very standard way, we developed this software in the front end, the same as the other approaches. We used a version of ICP, iterative closest point, to register consecutive point clouds. And then the edges between these point clouds, we had them create a sparse factor graph in the back end for post-graph optimization. And for loop closure, we wanted to take advantage of a CNN-based or deep learning-based place recognition approach. We use efficient segment matching, which is a kind of segmentation-based approach or local feature-based approach for place recognition. So place recognition is a retrieval task. It means you have a database of point clouds, and then you have a query point cloud or target point cloud, and then place recognition goes and find the most similar point cloud in the database to the query point cloud. And at this level, we call it, coarse localization. Once this top candidate is true positive, then we would like to solve the relative transformation between these 2 point clouds. We call it metric or fine localization. So from now on, I use, these terms a lot, just for your information. And yeah, so we basically incorporated this CNN-based with our SLAM. And a good thing about ESN, because it is CNN, it is pretty light, so that you can train the network, freeze the network, and run it, on CPU. It doesn't need, GPU. But a limitation of these approaches, local feature-based approaches, is they are based on, point cloud segmentation. You have to segment, the point cloud. For each segment, you train, a local descriptor. And if you increase, scalability, if you think about a, mapping a city, for example, like Sydney, then obviously in your database, you're going to end up with millions of these segments. I mean, they're local descriptors. As a result, these approaches, in order to improve the efficiency, they rely on a kind of, initial pose to limit search. So this is a kind of, drawback of local feature-based face recognition techniques. So here I have a video. I'm going to demonstrate the performance of ESM. So in the beginning, when the robot goes to the course, a bunch of point clouds, accumulate to make, the reference point cloud, and after that, this colorized, point cloud is, the recent point cloud. We take it, as target. It will be segmented, and then based on ESN, we are able to register these segments to the reference point cloud. And this way, we are able to basically, detect loop closures in this mock-up orbit rig, which is relatively, a small scale area. So now, in the second part of the video, I'm going to show the demonstration of the full pipeline. So the task was the robot, it started at home, indicated, by a circle on the ground, and then the mission is it has to go back, to that place autonomously at some point. Currently, we were teleoperating, the robot. The robot, goes to the environment, and here you see once a loop closure is detected, those red edges indicate, loop closures in the 3D lidar slam. The robot again, revisit the environment, and again, we have more loop closure edges resulting in a globally consistent map. And at some point here, we requested the robot return home, and robot autonomously, by taking advantage of those loop closure edges, find the shortest path to return home. And it's relatively ended up, within the circle. So with that experience and knowledge, I gained from Oxford University, I joined CSIRO, where I became familiar, with Wildcat. Maybe, you've heard of Wildcat. I'm going to describe it, briefly in the upcoming slides. But Wildcat, has really nice capabilities. One of them is a multi-agent, capability. And building upon these capabilities, we basically unleash, our ambition. And now, the target is addressing, some tasks as such: multi-agent SLAM, multi-agent navigation, accurate mapping, like, HD map, semantic understanding of the environment at a CT scale, at a larger scale, as well as, multi-agent re-localization without putting any kind of, constraint about the location of the robots in the environment. So robots share information at some point, and then basically they should be aware of their location relative to one another. A little bit about lidar SLAM. Maybe you've seen, these slides, because during my talk at ICRO 2022, I went through these slides. But briefly, Wildcat is a lidar inertial SLAM system. It's inspired by pioneering works conducted by Michael Bossi, Robert Zalot in 2008, 2009 in CSIRO. And it is highly versatile and robust, tested heavily, on different data sets in different environments, on different robot platforms, and it is really cool. And it showed 0% deviation in a sub-T DARPA final price. Maybe you watched, those videos, from DARPA, or you can just, check them out in DARPA channel on YouTube. And based on Wildcat, two companies spawned out of CSIRO: Automap, focusing on surveying applications, and MSN focusing on aerial mapping and aerial applications. A little bit about what is going on in Wildcat under the hood. Wildcat is modular based, and three main components of Wildcat are Wildcat odometry at low level. We integrate inertial measurements with lidar measurements in a kind of a sliding window to make some submaps of the environment, local maps of the environment. We call them, Wildcat frames. And at a higher level, we have a post-graph optimization. Again, we call it Atlas, where we have, nodes and corresponding frames for those nodes. And every time a loop closure is detected, we just, update these nodes at the Atlas level. And we have an offline component called global trajectory optimization. It looks like a kind of like a bundle adjustment in photogrammetry. It means Wildcat takes advantage of all the constraints, inertial constraints as well as lidar constraints throughout the trajectory to generate very accurate map of the environment. Mainly it is used, for surveying applications where speed is not number one priority and precision or accuracy is number one priority, right? So that was, a little bit about Wildcat. And when I joined, CSIRO, I wanted to become more familiar about, Wildcat and what is going on. And I kicked off a data collection campaign based on the perception packs here. By the way, we have, a spinning perception pack as well as, flat pack. The spinning pack, I had a conversation, with one of you. This is CSIRO design. We put a shin with 45-degree angle to improve, the vertical field of view. And this lidar spins using a mechanical servo motor. And this is, the difference with flat pack. Flat pack has just, the stable vertical field of view, which is, 32 degrees for Velodyne VR6. So based on these two perception packs, we collected a massive data set across our site, QCAT in Brisbane, indoors, outdoors. We have, diverse environments. We have a sparse forest area, dense forest area, structured environments, and also we went through the buildings. We have, multiple storage, very confined areas, like, for example, staircases, challenging SLAM systems. And we uniquely deployed, mounted, these retroreflective targets across the site. And in a kind of sweeping action, we try to scan these targets to be visible, in the maps. Then we detected, these targets, and also these targets were measured using, surveying tools. So we have, ground truth. We have the measured position of these targets, and in total, we could detect 63 targets across the site. And based on these targets, we could compare or we could evaluate, maps of Wildcat output, fast LEO2, as well as LIO SAM. So these are like, a state-of-the-art lidar SAM systems. And Wildcat showed its superiority, in these maps. Yep.
Is this the Atlas one or is the
This is the online one. Online one.
The Atlas.
Yeah. For the for the sake of fair comparison with LIO SAM and fast LIO2, we just basically got the map generated on the fly, and after that we did the comparison for the online app. And after this thorough evaluation and thorough comparison with a state-of-the-art SOTA, we decided to participate HILT Slam Challenge, organized at ICRA 2022 by HILT and the other university partners that time, Oxford University, and I think University of Zurich, if I'm not mistaken. And the Wildcat achieved the first place, and it was a big win for us, for the team. And on the left-hand side, you see the output of Wildcat for these construction sites with all the details. So, all right, so that was about Wildcat vanilla, and from now on, I'd like to talk about my contributions. I wanted to, on top of these capabilities of Wildcat, enhance the performance even further. So so that's why now I talk about place recognition, scan context. Maybe some of you are familiar with the scan context, a handcrafted approach, very common in Islam. And the idea is you define a disk around the sensor of lidar, and this disk will be split in some rings as well as sectors. And then for each beam, you store just the maximum height of the points residing in that beam. So this way you can create a global descriptor for your point cloud. So we call it end-to-end place recognition. It means for point cloud, which is the input, now you have an output, which is the global descriptor. You encode your point cloud descriptor, right? So this method is quite common, and that's why we wanted to develop it as a plugin alongside the other place recognition, mainly deep learning based in Wildcat ecosystem. The recommended resolution for a scan context is 20 rings by 60 sectors. And if you increase the resolution, obviously your global descriptors would be finer for place recognition tasks, right? However, it requires higher computation, so efficiency drops. So we developed this integration with Wildcat, and now I'm going to show you. This is, by the way, on a public dataset, MoldRAM, released for place recognition tasks. On the left-hand side, we have Wildcat vanilla. Again, loop closure works, but that is based on Euclidean search. It doesn't take advantage of place recognition. On the right-hand side, we have a scan context enabled, and those frames, they show the position of the query or target and the position of the top candidate. Sometimes, top candidate is like false positive, because along the path we have repeated patterns like similar bridges, similar tunnels, similar sections. So that's why place recognition, or all the place recognition approaches detect those places as true positive, right? But you see, based on place recognition, the drift, which is quite significant, such that based on Euclidean search, this drift is not detectable. As a result, there isn't any loop closure detection. But on the right-hand side, we see after a scan context detecting loop closures, the map becomes globally consistent. So this is another interesting sequence of MoldRAM called Sejong. Interesting characteristic about Sejong is it was scanned on a car traveling across a highway, including tunnel sections and some bridges. And there is a small overlap at the end of the trajectory. And by the way, the cell size here is 1 kilometer by 1 kilometer, which means the traversal, the length of traversal is about 25 kilometers. But when a scan context is enabled, it is possible to detect this loop closure and remove this drift, which is quite significant. This is a comparison on a trajectory of another sequence of MoldRAM called Riverside compared to the ground truth. Again, we see importance of place recognition. But a limitation about these handcrafted approaches, scan context, is the descriptor is not rotation invariant. And that's why we'd like to explore deep learning to make the descriptors invariant to rotation, right? So we switch our focus toward end-to-end deep learning based lidar place recognition approaches. As I said, ESM or those segment based place recognition approaches, they have difficulty in terms of scalability. Handcrafted approaches, they don't show rotation invariance, in their place recognition, in their descriptors. So we came up, with Log3D-Net, locally guided global descriptor learning for 3D place recognition. By the way, the code is available. I will give you the link to our GitHub. So we use quadruplet loss here. It means for anchor we have positive, negative, and a point cloud, which is dissimilar to these two positive and negative. And we use a sparse convolutional unit as the backbone to create these local features. And in order to aggregate these local features to make a global descriptor representing the point cloud, we use second order pooling. And I'm not sure, you guys, how much you are familiar with pooling approaches, but we have second order pooling, we have first order pooling, like for example, average pooling, max pooling. These pooling approaches, they are, first order. But a benefit of second order pooling is you can take advantage of covariance properties, for example, when you aggregate, local descriptors. So this increases the distinctiveness of the descriptors, right? And another contribution is adding this local consistency loss to make the local descriptors of anchor and positive close to each other as a constraint in feature space. Okay, again, this improves the distinctiveness of descriptor, the app. And it is quite common in end-to-end approaches. The dimension of global descriptor is 256. So now we've got 256 to store in the database compared to a scan context, which is the low resolution 20 by 60, 1200 elements. Here we've got just 256 elements. So these approaches, in terms of practicality, looks more efficient or memory efficient, right? So here, I've got a video to demonstrate the performance of, maybe I can just skip these parts of the video. Yeah, this is again, on Moran sequence DCC03. The robot starts, or the car starts, from this point. So I'm going to show you the success of end-to-end place recognition approaches in reverse revisits. Here we've got forward revisits because the direction of robot for the initial session was this way, and then for the revisit again, it is forward. And every time point cloud flashes green, it means Log3D-Net was successful in place recognition, and every time it is red, this is the interesting side, which is reverse direction. And when it flashes red, it means it missed the place recognition true positive. But overall, along this sequence, Log3D-Net was 88% successful, in terms of place recognition tasks. So this is another sequence on KT dataset sequence 08, one of the most challenging sequences, I believe. An interesting characteristic about this trajectory is orthogonal revisit. Now we're going to see that when the robot comes back to this point, it is a kind of like orthogonal. Again, another way to examine your place recognition approach to see how much it is invariant to rotation. So most of the time, Log3D-Net is successful to recognize place. So after this long loop, again, another orthogonal revisit happens, and plot tree the net, is successful. Again, overall for the sequence, 89% log tree net was able to recognize new places, right? ICRA 2022 was quite productive for us, for the team. For another event, another workshop, we participated in general place recognition, CT scale UGV localization, organized by Air Lab at Carnegie Mellon University, I believe, where we got the second place for place recognition task. So that was about a kind of place recognition for single agent scan. But in this work, I'm going to talk about deep, robust robots relocalization. In short, we call it R3 And what motivated us for this work was during the SOPTI challenge final prize, all the teams had to start their robots relatively close to each other to allow ICP to have a good initialization to merge maps generated individually from the robots, right? But we wanted to relax this constraint. We wanted robots to localize themselves relative to one another without knowing the location of their start point. Okay, so that's why we came up with R3 log. This is an IROS work for last year, I believe. So this is an overview of the pipeline. We wanted to address multi-robot relocalization as well as the wake-up problem. I guess you are familiar with wake-up problem. Wake-up means you have a prior map of the environment, and now robot comes to this environment, and it needs to localize itself against this prior map first to do downstream tasks, right? It is called wake-up problem in robotics. So basically, we've got one initial session. The robot goes to the environment, explore the environment, and then the second time in revisit session, it goes, and then you power up the robot for the first map, submap query. Now you need to find the top candidate from the prior map, and then upon that you are able to do relocalization. So again, thanks to Wildcat, we are able to store our maps as a kind of post graph, including the frames as well as the positions of the nodes, right? In memory, for example, or in disk, something. And when the robot goes to the in revisit session, when it turns off, when it turns on, then you're going to have one frame, the first frame. We use a deep relocalization approach to do localization, to solve localization problem. And before adding this information to the existing post graph, first we need to examine it, because if this place recognition was wrong, it means the top candidate doesn't represent the same environment, then it could cause serious issues in post graph optimization, because it would work as an outlier. So we need to examine the information first, and after that, once it is healthy, and basically we need to do a kind of sanity check. So then we have this deep verification where we take advantage of multimodality, or I call it cross modality. I will describe what this cross modality is in the upcoming slides. For this relocalization part, we use an adopted version of EGO-NN. EGO-NN is again a kind of end-to-end place recognition, but in conjunction with a global descriptor, it trains some local descriptors as well. So you use the global descriptor for coarse localization, and you use the local descriptors because you have the key point of the local descriptors to be able to use, for example, ransack to solve, the transformation between the target point cloud, query point cloud, and the top candidate point cloud. Okay, because we need, that relative transformation to be added to the post-graph optimization as loop closure, inter-loop closure in this case, right? So EGO-NN, we trained it because our target in terms of environment is natural environment. We have a data set called Wild Places. We collected, a massive data set in some national parks across Brisbane, Queensland, and we relied on Wildcat to generate, the grand truth. Feel free, you can check it, Wild Places, because I mean it is public and it is available for use. And for this deep verification, the idea is on the perception pack, as I said, we have cameras as well as the lidar scanner, and we know the calibration between these sensors. Currently, we rely on the front camera as well as lidar. So given the calibration parameter, it is possible to project either pixels on the point cloud or the other way around, right? So we get this relative transformation from our deep re-log. Then we examine this relative transformation by projecting the point cloud of the top candidate from initial session onto the query image, whose time stamp is the same as the time stamp of the query point cloud. So if they match perfectly, it means your re-localization is accurate. Coarse localization is done successfully, and metric localization is precise. If there is a kind of shift or misalignment on these two, it indicates something is wrong, right? So we'd like to basically figure out those unmatched cases and classify match cases, from unmatched cases. So that's why we use an approach called self-supervised superpixel-driven lidar representation. In short, it is called, a SLiDAR. A SLiDAR is a CVPR work with Sautier et al. And originally, it was proposed for object detection as well as semantic segmentation. But here we changed, the task for, matching between two modalities, image and lidar. So again, in our wide place data set, we have, this kind of scenes, and given the calibration, we are able to segment, our image. For each segment, we call it, superpixel. You can use a kind of, approach. There are, lots of approaches, non-deep learning approaches. You can use like, a slice to segment, your image. And because we are able to project, these points onto the images, therefore, it is possible, to find, the correspondences in 3D, right? So we have superpixels and superpoints. So based on superpixel and superpoints, we have, we define, 3 scenarios. On top, we have the scenario where coarse localization is successful and metric localization is accurate. It means there isn't any misalignment, right? And image and lidar both represent, the same environment. And we observed, if we look at, the similarity matrix between the local descriptors of superpixel and superpoint, there is a high correlation on the main diagonal. This is a nice observation, or a good indication about the correctness of place recognition, the success of place recognition. And another thing, we did in Euclidean space on the images. This is, a feature space, comparison between features, and this is, a Euclidean space. On the image, what we did, for every superpixel, based on the local descriptors in feature space, we find the top, superpoint candidate. Then we project the centroid of that superpoint onto the image. If it falls within the corresponding superpixel, we count it as a match between superpoint and superpixel. Otherwise, it is misaligned. Okay, so this is another case where place recognition is unsuccessful. Therefore, metric localization doesn't matter because image and point cloud don't represent you in the same environment. So in this case, we don't see that nice pattern on the similarity matrix, and then here everything is missing. There isn't any pattern observed. And this is the case when lidar and image they represent the same environment. That means place recognition is successful, but there is a shift, or the metric localization is not accurate, or it is wrong. Therefore, we have a kind of pattern in this Euclidean space, right? So based on these observations, we defined two metrics: mean cosine similarity as well as alignment ratio. And for these metrics, we trained a very simple classifier to classify matched, from. And this is basically our deep verification line. And here, we've got two cases on top. So these are, based on, data, from robots in real time. On top, we have successful metric localization. And here, this case basically, pass our verification successful. Whereas in this case, there is a kind of shift between two modalities, and this didn't pass. So now here we've got a video. Hopefully, my internet speed allows us to see the entire video. So the goal here is robot relocalization to address vehicle problem. One robot goes to the environment as initial session, and second time as a revisit session, with a decent time difference between these two sessions to see different lighting conditions. So it seems my internet doesn't have a good speed here. So before relocalization, map is a bit blurry, and DPR is performed between revisit and initial sessions, and relocalization first is validated before merging maps. And once metric localization got approved, both maps merged, resulting in a globally consistent map. It means in this case now, the agent from revisit session knows its location against the map generated from initial session. This is the case where when robots started pretty far from each other, 40 meters apart. A quadrupedal robot on top from Boston Dynamics, and this tracked robot. Tracked robot starts again, from home indicated with that helipad. So the idea is after relocalization, agent R5 should autonomously go to the origin of agent R1. So before relocalization, obviously both maps start from origin, and around that tree, robots share information. Relocalization is done, and Wildcat merges maps. And from this point, we say R5 go back home autonomously, and the robot takes the path to come back to the origin of R1. So that was about deep relocalization. And this is my recent work. I call it PGAT, Post-Graph Attentional Neural Network. So far, it is quite common in deep learning community, in place recognition community, that you do a comparison between pairs of point clouds, but you can't take advantage of temporal information or temporal correlation between consecutive point clouds, for example. So the idea here was I wanted to compare pair of subgraphs, and these subgraphs, they consist of sequence of point clouds, and PGAT is a kind of backbone agnostic. It means it can be integrated on top of the existing end-to-end place recognition approaches, like for example log3D map. Then what we store these global descriptors 256 by 1, but just pairs of subgraphs, and we'd like to compare pairs of subgraphs using attentional graph neural network to maximize spatial temporal information. Okay, so this is the idea that you get. So this is an overview of the entire approach. Wildcat or any SLAM system, lidar SLAM system, they give us these point cloud frames. Then they go through this backbone. We encode them, generating those embeddings, global descriptors, and we record those global descriptors along with positional information of these nodes using some deep libraries, like for example DGL, if you guys are familiar with. And eventually in the database we're going to end up with n subgraphs. We generate pairs of subgraphs out of these subgraphs, and then now these subgraphs go through this model attentional GNN. And attention,
So again, how are the subgraphs defined?
Yeah, based on travel distance. So we say, so
Okay.
that's why I like pose graph, because we assume you have a lidar SLAM system in which you can get the robot pose for 100 meters, for 200 meters without significant trip.
So from the trajectory color coded.
Yes, yeah.
You can do it in information space.
Yeah, but when you use attention mechanism, you need to know the positional information between tokens. And currently, we get that information from a system like, for example, odometry
So
or SLAM.
if at some point on the trajectory someone stops the laser,
Yeah.
and,
Then you just pick one keynote, for example. You don't have to store all the nodes representing the same place. Yeah. So that's why we tested our MolRAN, and MolRAN again is different from Oxford, which is quite common in for place recognition tasks. And MolRAN literally release the scans at 10 hertz, but the same as keynote extraction, you can just extract those keynotes and just keep them in your database.
so you say position.
Position.
So orientation doesn't matter.
I think for attention, orientation doesn't matter as long as because it must be relative.
But how about uncertainty of that position?
So this is the thing. Our assumption is over the course of 100 meters, 200 meters, lidar odometry without any loop closure can give you an acceptable level of accuracy. And it works out, to be honest, for our attentional GNN. But that's a good point. So after that, we use a kind of similarity metric, cosine similarity, to generate a prediction, and we have grand truth. Obviously, it comes from grand truth. And we change place recognition task to a classification task. So we call it multi-label binary classification, and we use a cross entropy loss to train the network. So this is a breakdown of the entire pipeline. Here we have a set of global descriptors for subgraph A, positional information subgraph A, as well as, the information for subgraph B. This is, the block of attentional graph neural network. We've got, multiple layers of attention here. And we use intra-attention as well as inter-attention. So attention mechanism is a kind of like, mapping function. You have, query, you have key value, and basically you make, a weight based on, query and key, and multiply it, by value to find, attention score between, tokens. And intra-attention mechanism deals with the relationship between nodes within one sequence in order to improve the distinctiveness of these descriptors to make them invariant to viewpoint, for example. So we call it, contextual information aggregation. While inter-attention mechanism deals with the relationship between nodes across two subgraphs in order to, recognize, places in revisit areas, right? And again, this part is just, binary cross entropy. And because, we use cosine similarity, the similarity values are going to be between -1 and 1. We use, this linear algebra to shift them between 0 and 1. Because, we talk about, binary classification 0 and 1. So in terms of experiments, we trained, the network on different data sets. Oxford data set, as I said, quite common. This is not, by the way, the original Oxford data set from Paul Newman. This Oxford data set is used mainly, for place recognition, curated by the authors of PointNet Milad in 2017 for the purpose of place recognition. And they added, in-house some sequences of data set captured somewhere in Singapore, to have basically, this output distribution or data from two different environments to challenge, the network in inference or for test. And we added, Moran because Moran again, has its own characteristic. So on top of these SOTA approaches, PointNet, Milad, MinClock, 3D, PPTNet, each has a different type of backbone. PointNet is based on PointNet backbone. MinClock is CNN based, and PPTNet is transformer based. So that's why, we say PGET is agnostic. On top of these descriptors, we trained, PGET and compared the results with baseline. I'm not going to go through all the details in this table, but in summary, PGET shows more than 10% performance gains when integrated, with these approaches. And also PGET shows more consistency in terms of, domain shift. That means when, the sequences, the data, they are, out of distribution. So, the generalization capability of the network, matters a lot for us. We don't want to train the network, for every new environment. So that's why, we'd like to improve the generalization capability of the network. So here I've got, some recall plots on Oxford and in-house data sets. The purpose of this experiment was I trained, the networks, PGET as well as your baselines 5 times with the same setting to see how deterministic the networks is. But to be honest, these networks are not deterministic. They show a kind of indeterministic behavior. But variance analysis is quite interesting. As you see, PointNet Milad, although it is pioneer in place recognition, it shows very high variance when you train it a few times. PGET shows an acceptable level of variance compared to MinClock and PPTNet, and also recall curves show superiority of PGET in improving accuracy and stability in place recognition. Here, I brought 2 examples of retrieval. On the left, we have query point clouds. On the right, they are the top candidates selected by PGAT, min-cloud, PPT9. And as you see, these scenarios are quite challenging because point clouds literally don't have informative features. So it is difficult for face recognition. But thanks to taking advantage of temporal information for these cases, PGAT works more efficiently. And here I've got a graph displaying the behavior of attention mechanism. So we've got two subgraphs with some overlap between two nodes. So in layer 0, as you see, this is the receiver node. For attention, we can't see a nice pattern because we say if point clouds are nearby, attention score should be higher. And by the way, the attention scores you can see the different shades. Blue shade for cross attention, whereas gray shades for self attention or intra attention, inter attention, right? When we increase number of layers, after a few iterations, we see an acceptable pattern in terms of attention scores. So this shows attention mechanism is really powerful in terms of contextual aggregation. Okay, so this is the last slide, and let me wrap up my presentation with a few takeaways. They are based on personal experiences. So I believe data-driven models. I had this conversation before the presentation. If we integrate them well with model-based approaches, then in a hybrid way we can take advantage of both to improve robustness, to improve scalability, to improve accuracy. GNN, graph neural network, and transformers are really well suited to for post-graph based SLAM systems, because graph neural network requires the properties existing in postgraphs. And most of the lidar place recognition networks, they downsample the point cloud significantly. So the golden number is 4096. And most of these approaches, they downsample, for example, for lidar Wildcat, each frame online consists of 20K, 30K points, but you have to downsample to the point cloud to 4096. So literally in natural environments, these points, can be noisy points, for example. So we'd like to relax this number of downsampling points with one of my PhD students. And also we'd like to address ground area re-localization and add this capability to Wildcat, another PhD topic we are working on. All right, so thank you very much. Thank you for your attention. If you are interested, you can just check out the GitHub CSIRO Robotics. White Places, the second version with the images white scenes for semantic stuff, as well as the code of PGAD log3dnet. They are publicly available. Thank you so much.
Nice. Questions? Jesse.
Thank you. Very interesting talk. I've got two questions, both related to the attention network part. The first one is, because it seemed that that network basically operated on sequences of features. Is that correct? Or like you have the point clouds and then extract feature nodes from them?
For attention.
Yes.
So we have basically, intra-attention. Intra-attention takes care of, the information between sequential point clouds, whereas inter-attention takes care of attention between, the nodes across two subgraphs.
I was wondering, do you think a method like that could be extended to features for representation you get from visual SLAM? So like key point features.
Yeah,
absolutely. Like 2D.
Yeah. I believe this PGAT can be applicable, for visual SLAM as well. But to be honest, I was thinking about it, but the problem with visual SLAM is there is no guarantee after 100 meters. When you collect, a sequence of nodes, your positional information is still accurate enough to be used in attention mechanism. So that's why I put emphasis on lidar odometry.
Yeah, because you need pose information.
Pose
that's accurate,
information,
right?
exactly.
And my second question is, how do you think the attention network would respond to situations with lots of changes, like slow term changes, like change detection, or a situation where it comes back and large portions of the environment has changed?
So yeah, that is a good point actually. Especially for place recognition, you try to train the network so that your global descriptors should be kind of invariant, to those temporal changes. So as I said, our focus now is natural environments. In natural environments, when you start at this point, if it is windy, you're going to have lots of dynamic motions, for leaves, but eventually your global descriptor should capture these temporal changes and make the descriptor invariant to these changes. Or for example, again, scene graph, for example, hierarchical way. So we were thinking about it. Let's say, for example, you start from a car park full of cars, at a time of a day. Then when you go back, the car park is empty. So your descriptor should capture, the structure of the car park instead of, those cars. Yeah. So that's why, again, seg match or efficient segment matching, ESM, or those feature-based approaches, they are really sensitive, to these features. So they basically grab, some local features, from cars or from objects in the scene. So you need to design, the network in a way the network becomes invariant, to these things. But again, multimodality, fusion of camera with lidar can be really helpful to detect, these dynamic entities and just, exclude them, from the scene and just, focus on aesthetic features.
Thank you. Any other questions? I do have one.
Yeah.
Why do you do the demonstration of the more randomized that recent results in scan context? Is that different?
So it has a story. But I believe more RAN. So a feature about more RAN is it became public, for the purpose of place recognition, and there isn't any raw spec in the database. Then some SLAM people, they came and then they developed some tools to create raw specs from the information. And for the point cloud fields, interestingly, there is no timestamp for individual points. And most of the approaches like LeoSAM and FastLeo, they're super sensitive to the timestamp of individual points. And we wanted to show, because there was a criticism about Wildcat being very sensitive about those timestamps. But here we showed that Wildcat still works pretty well, really not in this data set without the presence of timestamps.
I'm just curious, the situation when scan context was not enabled and the loop closure failed, just from the geometric or the Euclidean.
Yeah, because that is based on Mahalanobis distance.
Yeah.
You compute the covariance uncertainties, and based on the uncertainties, you define a search radius, and you say now all those neighbor nodes falling in this search radius, just you evaluate loop closure detection for those nodes. Okay. But in this case, the drift is larger than your search radius, obviously, and relying on those Euclidean-based approaches, you are not able to close the loop.
But so if the drift is Larger than the search radius, it means that you don't estimate correctly the variance.
Yeah, it's true.
So,
Yeah, but in practice, it is quite challenging, to because currently, GTSAM or all these postgraph optimization libraries, they basically propagate error. They estimate or predict, uncertainty. But this shows sometimes, the uncertainty estimated, it is not, the same as what exists in reality.
shouldn't be. So this is what I'm trying to say, that the estimation problem is.
But you have to, at a CG scale or at that larger scale, you have to kind of shrink, the search radius. Otherwise, in terms of efficiency, it's not going to be, super efficient. If, let's say, for example,
covariance is giving you.
Yeah, correct. But let's say, when your covariance covers the entire nodes, then, Euclidean base, cannot manage in terms of.
That's situation when you are completely lost and you do re-localization.
Yeah.
It covers the entire nodes, but it should, theoretically, it should give you good information of where to search.
Yeah.
I presume
Theoretically.
the random covariance between nodes was a fixed value, the odometry noise.
So you based on, let's say, manufacturers of those sensors, you define, some measurement noise, standard deviation, put it, in your optimization, then you can estimate a posteriori uncertainty, right? But in practice and theory, they don't read well sometimes. But again, I'm saying, even if in theory you can estimate, uncertainty pretty well, but your covariance, if there isn't any loop closure, imagine, for example, the trajectory is a straight line.
So covariance is infinite, so you cut it at 3 sigma, 2 sigma, whatever you want to.
Yeah. So let's say if you cut it, 1 sigma, 68% level of confidence, but again, you're going to end up, with a situation that you have to examine pairs of nodes, repeatedly so many times, decreasing, the efficiency of the approach. So that's why, we'd like to explore, place recognition, because it goes, in feature space, find, the top candidate, and it limits, the search significantly.
But there is a search in place recognition as well, right? Because all the descriptors.
Yes, but that is in feature space. You have, let's say, a stack of those descriptors, 256, and now you compare the descriptor of the query point cloud with that stack of descriptors using, for example, KD or FLAN. But still, it is much more efficient than, evaluating 2 nodes pair by pair, and then find, the loop closure, right?
Definitely you should use both. So that's the point, right? So you should use the location, the uncertainty in the location, and then that will define, okay, I'm close to these regions, so I compare descriptors with this region, but I don't need to compare.
Yeah, definitely, you need to use, a combination of both. But once you basically get the top candidate, then you can basically examine that top candidate using, for example, model of distance and this sort of things, and see whether, that node falls within, this uncertainty or not.
I would say the other way around, but it's easier. So,
Do we have any question online? No, that's pretty much.
Wait, hello, can you hear me?
One sec, let me turn on your camera. Oh. If you want, you can also switch on your camera if you want.
Okay. Hi, this is Chen Hao, and by the way, great presentation. I'm just curious about 2 things. First is in the log G 3D net, I noticed that there are multiple hints during the visual odometry when you were running the face recognition. Well, how will you use these multiple hints to fuse into the current map? That's the first question.
Multiple things you said, sorry?
Multiple hints.
Oh,
yeah.
Oh, yeah. So if there is a redundancy, in multiple hints, again, you can define a threshold. Okay. So if there are multiple place recognitions occur in one part of the trajectory, so one would suffice to remove drift, right? So basically, we filter out redundant loop closure information, and eventually, we add just some of those information in order to remove drift. Because if you detect the loop closure and add this edge to your post graph, it would be sufficient to close the loop. Did I answer your question?
Yeah. Yes. Yes. By the way, another question is, I think since you are focused on the place recognition and post graph, and how would you will you in the future involve the knowledge from visual language models? I think these models demonstrate quite a lot of in concept and knowledge learning. Will that be beneficial to these place recognition challenges?
Yeah. So that is the roadmap. So that's why we have Wild Scene, the second version of Wild Places, where we've got images corresponding to the frames, as well as semantic labels. But this multimodality definitely is quite interesting, and we'd like to explore it. But we need to take it into account that hardware limitation is a thing when you think about real-time operation on the robots, right?
Yeah. Yes, I think the real-time performance is one of the main concerns. But thank you. That's all of my question.
Yeah, thank you for the questions.
Right.